A very good morning to all of you. Myself Anju, PGT Chemistry from Government Senior Secondary School Badwasani, Sonipat. My mentor name is Dr. Jyoti Arora. Today I am here in front of you with the topic of class 12th chemistry, surface chemistry, and the part is catalyst. So students, today we are here to discuss about catalyst. Topics to be covered in this class are catalyst, type of catalyst and use of catalyst, promoters and activators, catalytic poisons and inhibitors, homogeneous and heterogeneous catalysis, selectivity and zeolites. So firstly, we have to understand actually what the catalyst is. So students, catalyst is a substance which changes the rate of a chemical reaction without itself undergoing any chemical change is known as catalyst. And the process in which a catalyst is used is known as catalysis. Now, with the help of this reaction, the reaction is potassium chlorate when heated strongly decomposes slowly giving dioxygen. The decomposition occurs in the temperature range of 653 to 873 Kelvin. However, when a little of manganese dioxide is added, the decomposition takes place at a considerably lower temperature range at 473 to 633 Kelvin and also at a much accelerated rate. The added manganese dioxide remains unchanged with respect to its mass and composition. In a similar manner, the rate of a number of chemical reactions can be altered by the mere presence of foreign substances. So, the systematic study of the effect of various foreign substances on the rate of chemical reactions was first made by Berzelius in 1835. He suggests the term catalyst for such substances. So we can say that catalysts are the foreign substances which enhance the rate of reaction, which accelerate the rate of reaction without changing its mass and in composition in that particular reaction. So we can say that catalysts are the foreign substances which increase the rate of reaction. So the substance which accelerate the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalyst. The phenomenon is known as catalysis as we discussed earlier. Now the question is, why we study catalyst in surface chemistry? The question is, why we study catalyst in surface chemistry? Because the working of catalyst is based upon surface phenomena of catalyst. In the mechanism of catalyst, surface phenomena is involved. So catalyst is also considered as part of surface chemistry. Now next is promoters and activators and catalytic poisons and inhibitors. As the name indicates, promoters, who promotes? The substance which increase the activity of a catalyst is called as promoters. Like molybdenum is a promoter in Haber's process. Haber process is generally used for the formation of ammonia. The substance which decrease the activity of a catalyst are called poisons or inhibitors. Cobalt is an inhibitor in Haber process, in the same process as we discussed in case of molybdenum. So cobalt is inhibitor in Haber's process and molybdenum is the promoter in Haber's process. Now next is homogeneous and heterogeneous catalyst. We hear this homogeneous and heterogeneous at a lot of time in many classes, in English, in mathematics, in chemistry or in physics. But here the term homogeneous and heterogeneous catalyst is considered under catalysis. So homo, as the name indicate, is same, and hetero, as the name indicate, is different. So let's discuss the homogeneous and heterogeneous catalyst. Homogeneous catalysis. The catalysis in which catalyst and the reactant are in same phase is called homogeneous catalyst. Like if the reactant is in gaseous phase, so the catalyst also is in gaseous phase, is known as homogeneous catalysis. Or we can say that when reactant and product and catalyst are in same phase, the process is said to be homogeneous catalysis. The example is oxidation of sulfur dioxide into sulfur trioxide with dioxygen in the presence of oxide of nitrogen as the catalyst in the lead chamber process. As you see in the picture, the reaction, when sulfur dioxide is treated with dioxygen in the presence of a oxide of nitrogen as a catalyst, it gives us sulfur trioxide, and the process name is lead chamber process. Here the reactant sulfur dioxide and oxygen and the catalyst nitric oxide are all in the same phase, and the phase is gas. So they are known as homogeneous catalysis. Second example is hydrolysis of methyl acetate. As you see in the picture, this is methyl acetate. Hydrolysis of methyl acetate is catalyzed by hydrogen ions furnished by hydrochloric acid. Here we use catalyst is hydrochloric acid. You see, both the reactant and the catalyst are in same phase, in liquid phase. So this is also an example of homogeneous catalyst. Hydrolysis of sugar is catalyzed by hydronium ions furnished by sulfuric acid, and both reactant and catalyst are in same phase. This is liquid phase. So this is also an example of homogeneous catalysis. Now the theory of homogeneous catalysis. According to activated complex theory, a catalyst combines with reactant to form activated complex, which decomposes to form product and itself regenerate. Catalyst increase or decrease the activation energy or energy barrier and hence change the rate of reaction. This is known as activated complex theory. Now, heterogeneous catalyst. As the name indicates, hetero means different. The catalytic process in which the reactant and the catalyst are in different phase is known as heterogeneous catalysis. The first example is oxidation of sulfur dioxide into sulfur trioxide in presence of platinum. As you see in the picture, the reaction, sulfur dioxide oxidation held in the presence of a catalyst platinum, and it gives us sulfur trioxide. The reactant is in gaseous state while the catalyst is in solid state. Both are in different states, so it is known as heterogeneous catalysis. Next example is combination between dinitrogen and dihydrogen to form ammonia in the presence of finely divided iron. Iron is catalyst here, and this process is known as Haber's process. Here the dinitrogen and dihydrogen are the reactants are in gaseous phase, and the iron is a catalyst which is in solid phase. So this is known as the heterogeneous catalysis. Third example is oxidation of ammonia into nitric oxide in the presence of platinum gauze is known as Oswald process. You see the reaction, ammonia when react with dioxygen in the presence of a catalyst platinum gives us nitric oxide and water, and this phenomenon, this process is known as Oswald process. The reactant are ammonia and dioxygen in gaseous state while the catalyst is in the solid state. So this is also an example of heterogeneous catalysis. Next is hydrogenation of vegetable oils in the presence of finely divided nickel as catalyst. Vegetable oils, when hydrogenated, it gives us vegetable ghee in the presence of a catalyst nickel. Here, one of the reactant vegetable oil is liquid and other of the reactant dihydrogen is gas, but the catalyst nickel is in solid phase. So this is also an example of homogeneous catalysis. Next is adsorption theory of heterogeneous catalysis. This theory explains the mechanism of heterogeneous catalyst. The old theory known as adsorption theory of catalysis was that the reactant in a gaseous state or in solutions are adsorbed on the surface of solid catalyst. The increase in concentration of reactant on the surface increase the rate of reaction. Adsorption being an exothermic process, the heat of adsorption is utilized in enhancing the rate of reactions. The modern adsorption theory is the combination of intermediate compound formation theory and the old adsorption theory. The catalytic activity is localized on the surface of catalyst, and this mechanism involves 5 steps, and the steps are: the first step is diffusion of reactant to the surface of a catalyst. Second step is adsorption of reactant molecule on the surface of a catalyst. Third is occurrence of chemical reaction on the catalyst surface through formation of an intermediate. Fourth point is desorption of reaction product from the catalyst surface and thereby making the surface available again for more reaction to occur. Fifth point is diffusion of reaction product away from the catalyst surface. The surface of catalyst, unlike the inner part of bulk, has free valencies, which provide the seat for chemical forces of attraction. When a gas comes in contact with such a surface, its molecules are held up there due to loose chemical combinations. If different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules. Thus, formed molecules may evaporate, leaving the surface for the fresh reactant molecules. This theory explains why the catalysts remain unchanged in mass and chemical composition at the end of reaction and is effective even in small quantities. It, however, does not explain the action of catalytic promoters and catalytic poisons. Now, you see in the picture, when a catalyst reacts with the reacting molecule, a reactant, adsorption of reacting molecule here, forming an intermediate formation. After intermediate formation, desorption of product molecule is there and product and catalyst both are separated by reaction in a product. Now, the adsorption theory in the surface of catalyst summarized as one of the reactant approaches the catalyst surface and settles onto an active site, and the process is known as adsorption. Another reactant approach the catalyst. Rearrangement of electron take place. The process is reaction. The product are released from the surface and the process is desorption. So this is summarized as a complete adsorption theory as we discussed earlier. Now this is a graphical representation of a catalyst. Here the graph is in between a potential energy and reaction coordinate. You see the reactant here and reactant completely change into a product by achieving the activated complex or highest energy level. With the addition of a catalyst, this reactant change into product easily. So this graph shows the activity of a catalyst by changing from reactant to product by achieving the maximum energy level activated complex. Next is, for example, now we take an example. A plus B a reactant gives us C plus Da product. This reaction complete in 20 minutes. But if we add some catalyst in it, time will change. It will increase or it will decrease, and it depend on catalyst we use. It is positive catalyst or it is a negative catalyst. So it means catalyst always accelerate the rate of chemical reaction. Whether it increase the rate of reaction or will it decrease the rate of reaction, it depends totally on the type of catalyst. If we use a positive catalyst, it increase the rate of a reaction. And if we use negative catalyst, it decrease the rate of reaction, but without getting consumed in a reaction. So we discuss here the two type of catalyst, positive catalyst and negative catalyst. Positive catalyst always increase the rate of reaction and negative catalyst always decrease the rate of reaction, but the point to memorize is without getting consumed in a reaction. Important features of solid catalyst. First is activity. The activity of a catalyst depends upon the strength of chemoabsorption to a large extent. The reactant must get adsorbed reasonably strongly onto the catalyst to become active. However, they must not get adsorbed so strongly that they are immobilized and other reactants are left with no space on the catalyst surface for adsorption. It has been found that for hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals, with maximum activity being shown by group 7-9 element of periodic table. As you see in the reaction, dihydrogen react with dioxygen in the presence of a catalyst platinum and it gives us water. Now, second point is selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product selectively. When under the same reaction conditions, many products are possible. Selectivity of different catalysts for same reactant is different. For example, starting with dihydrogen and carbon monoxide and using different catalysts, we get different products. Carbon monoxide, when react with dihydrogen in the presence of a catalyst nickel, it gives us methane and water. But when carbon monoxide with dihydrogen react in the presence of a catalyst copper, it gives us aldehyde, formaldehyde. Now you see with these two examples the selectivity of a catalyst. With the help of the use of two different catalysts in the same reactants, we get different products. As we use nickel as a catalyst, we get product as a product methane, and if we use copper as a catalyst, we get formaldehyde. Thus, it can be inferred that the action of a catalyst is highly selective in nature. Now, shape selective catalysis by zeolites. This is very important topic of catalyst. The catalytic reaction that depend upon the pore structure of the catalyst and the size of reactant and product molecule is called shape selective catalysis. Zeolites are good shape selective catalysts because of their honeycomb-like structures. Zeolites have a structure which is known as honeycomb-like structure, which resembles as honeycomb. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminium atom, giving aluminium oxygen silicon framework. The three-dimensional arrangement of aluminium, oxygen and silicon is as aluminium, oxygen, silicon framework. The reaction taking place in zeolites depend upon the size and shape of reactant and product molecule as well as upon the pores and cavities of zeolites. They are found in nature as well as synthesized for catalytic activity. So, zeolites are shape selective catalysts and they have three-dimensional network, and these structures of zeolites resembles the honeycomb, and the arrangement is in three-dimensional is as like aluminium, oxygen, silicon framework. They found in nature as well as synthesized. Zeolites are being very widely used as catalysts in petrochemical industries for cracking of hydrocarbon and isomerizations. An important zeolite catalyst used in the petroleum industry is ZSM-5. Important zeolite catalyst used in petroleum industry is ZSM-5. It converts alcohol directly into the gasoline by dehydrating them to give a mixture of hydrocarbons. Next is enzyme catalysis. Enzyme catalysis is also a very important topic of catalyst. Enzymes are complex nitrogenous organic compounds which are produced by living plant and animals. They are actually protein molecules of high molecular mass and form colloidal solution in water. They are very effective catalysts. Catalyze numerous reactions, especially those connected with natural processes. Numerous reactions that occur in the bodies of animals and plants to maintain the life processes are catalyzed by enzymes. The enzymes are thus termed as biochemical catalysts, and the phenomena is known as biochemical catalysis. Many enzymes have been obtained in pure crystalline state from living cells. However, the first enzyme was synthesized in the laboratory in 1969. Examples of enzyme catalyzed reactions. First example is inversion of cane sugar. As you see in the picture, in the reaction, the enzyme of invertase convert cane sugar into the glucose and fructose. With the catalyst invertase, the enzyme is invertase. Second reaction is conversion of glucose into ethyl alcohol. Here, the zymase enzyme converts glucose into the ethyl alcohol and carbon dioxide. We discussed two reactions here, inversion of cane sugar with the enzyme invertase and conversion of glucose into ethyl alcohol with the enzyme zymase. Now next example is conversion of starch into maltose. The diastase enzyme converts starch into maltose. Next is conversion of maltose into glucose. The maltase enzyme converts maltose into glucose. Next is decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzes this decomposition. In stomach, the pepsin enzyme converts protein into peptides, while in intestine, the pancreatic trypsin converts proteins into amino acids by hydrolysis. Next is conversion of milk into curd. It is an enzymatic reaction brought about by lactobacilli enzyme present in curd. I think all of these examples you see in your daily life, in your regular life, like the example of conversion of milk into curd, conversion of starch into maltase, conversion of maltose into glucose, decomposition of urea into ammonia and carbon dioxides are we discuss in our daily life, we see in our daily life. So the next is characteristic of enzyme catalysis. Enzyme catalysis is a unique in its efficiency and high degree of specificity. The following characteristics are exhibited by enzyme catalyst. First, they are most highly efficient. One molecule of an enzyme may transform 1 million molecules of the reactant per minute. They are highly efficient. Second is highly specific in nature. Each enzyme is specific for a given reaction. Example, one catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only. It does not hydrolyze other amides. So these are most highly efficient and most highly specific in nature. Next is highly active under optimum temperature. The rate of an enzyme reaction becomes maximum at a definite temperature called optimum temperature. On the either side of optimum temperature, the enzyme activity decreases. The optimum temperature range of enzymatic activity is 298 to 310 Kelvin. Human body temperature being 310 Kelvin is suited for enzyme catalyzed reactions. Next is highly active under optimum pH. The rate of an enzyme catalyzed reaction is maximum at a particular pH called optimum pH, which is between pH value 5 to 7. Increasing activity in presence of activators and coenzymes. The enzyme activity is increased in the presence of certain substance known as coenzymes. It has been observed that when a small non-protein enzyme present along with an enzyme, the catalytic activity is enhanced. The catalytic activity here is enhanced here. So they are highly active and they increase the activities. Next is mechanism of enzyme catalysis. There are a number of cavities present on the surface of colloidal particles of enzymes. These cavities are of characteristic shape and possess active groups such as amide and acids. These are actually the active centers on the surface of enzyme particles. The molecules of reactant which have complementary shape fit into these cavities just like a key fits into a lock. On account of the presence of active groups as activated complex is formed which then decompose to yield the product. Thus the enzyme catalyzed reaction may be considered to proceed in two steps. First is step 1, binding of enzyme to the substrate to form an activated complex. As you see in the reaction, enzyme combine with substrate to form an activated complex. In step 2, decomposition of activated complex to form product. You see in the reaction, decomposition of this activated complex into the product. Next, this process is known as lock and key hypothesis. Lock and key theory explain how enzyme works. As a particular key is always fitted in particular lock, a particular substrate is always fitted in a particular enzyme and form an enzyme substrate complex. Now next is catalyst in industries. These catalysts are used in various industries as we discussed earlier. The first industry is formation of ammonia by Haber process for manufacturing of ammonia. Second, here the catalyst is finally divided iron molybdenum as a promoter. In the process Haber process, we use the catalyst, they are molybdenum and finally divided iron. In Oswald process, for the manufacturing of nitric acid, we use Oswald process. The catalyst here is planetized asbestos. Third is contact process. For the manufacturing of sulfuric acid, we use the catalyst vanadium pentoxide. Vanadium pentoxide is the catalyst here in the contact process. So catalysts are used in various industries for the formation of ammonia, for the formation of nitric acid and the formation of sulfuric acid. So students, today we discuss about catalyst. What is the definition of catalyst? Catalysts are also known as foreign substances which enhance the rate of reaction, which always increase the rate of reaction, but they increase rate of reaction in two ways, in positive manner or in negative manner. If they increase the rate of reaction, they are known as positive catalyst, and if they decrease the rate of reaction, they are known as negative catalyst. After that, we discuss the type of catalyst, homogeneous catalyst and heterogeneous catalyst. In homogeneous catalyst, the reactant and the catalyst both are in same phase, and heterogeneous catalyst, both the reactant and the catalyst are in different phase. After that, we discuss about zeolites, which have three-dimensional structure and which resembles their structure as like honeycomb. After that, we discuss about the mechanism of enzyme catalyst, characteristics of enzyme catalyst, and the use of enzyme catalyst. In mechanism, we discuss the lock and key hypothesis, and after that we discuss about the catalyst in industries where we use catalyst. So students, now the time for assignment. So today your assignment is, what are catalysts? The first question is, what are catalysts and why they are studied in surface chemistry? This is around 5 to 6 lines. You give the answer of this question. What are catalysts and why they are studied in surface chemistry? This is of 3 marks. Question number 2 is, explain homogeneous and heterogeneous catalysts in detail with example. As we discussed earlier, homo means same, in which the reactant and the catalyst are in same phase, and in heterogeneous are different, in which reactant and catalyst both are in different phase. With example you give the explanation. What is shape selective catalysis? What is shape selective catalysis and what is the role of shape selective catalysis in this topic? Question number 4 is, describe some features of catalysis by zeolites. Zeolites are shape selective catalyst which have 3-dimensional structure, and the structure of zeolites resemble honeycomb as we discussed earlier. So you write this question. Question number 5 is, explain lock and key hypothesis in context of catalysis. You write this hypothesis in context of catalysis, how a lock and key generally react or act. Question number 6 is, explain use of catalyst in industry. How we use catalyst in industrial purpose, in Oswald process, in Haber process, and in contact process. 3 processes we discussed here. We use catalyst in industrial form. Question number 7 is, give some examples of catalysis. You can give the examples of catalysis, even 5 to 6 examples you have to write. Question number 8 is, explain activated complex theory. With graph you explain this theory and what is the meaning of activated complex and how it will work in catalysis, phenomena of catalysis. So the 8 questions are here for you for recapitulation and to write as an assignment, and we discuss these questions in next class. If you have any problem, you can discuss with me these topics, these questions in next class. Thank you.